how I do it.
I will be guarding you. You're not like, I will be guarding you.
I need a rematch with Ty. In the last year tournament with two house, like him and Rafa. He like just absolutely worked defense.
What?
How? I heard about
Exploiting Gyro?
It was bad. I gave it to him. Yeah, and he hasn't let me hear the end of it.
Oh.
Yeah.
Have you seen this?
No, bro.
No, that's funny.
Wait, this got changed.
Jason. Yeah, it did get
Shoot.
Okay, this was tier list and tier list. These are both in now.
No, now it's tier list of.
No, this-
That's just a tier list of any.
Tier list of ice cream tier lists.
Oh.
She was kind of balling yesterday.
Yeah, he wants you.
I will not hear it. I won't hear it.
He threw to Sean Spencer, little passes. Diving me up.
Those whiteboards are like toast. The blue is like tape down there. I don't really ever use those. so.
Well, why do
I've seen
you
that.
use it?
They think it's just like.
It's just there.
Huge stack.
I wouldn't have put it F, but I'd probably put it in the middle.
It's
When
like
you-
McDonald's. Yeah, what?
Yeah.
The golden hat.
I think Wendy's is
I've never been to one of these. And I don't really-
definitely better than Burger King. This guy
I
was.
just got me some water.
Yeah, a lot of water. What should we put water in? They put Cajun
Keep going.
water.
First team done.
Long John Silver.
I think Rich was like pencil.
Well, Rick Sixty is made better food.
Oh, McDonald's. Bro, Rich Henry, where's my pizza? Okay, look,
How
what
did
did
I burn it?
the timer going off on the picture very, very loud. I heard it, and I can't hear it.
I don't even remember that.
Yeah, that's because
Yo, it's,
it was, you very deliberately set up the Burger King.
I think one of these is, you gotta.
He did that.
like,
Yeah.
we should hit the tuners review session.
Oh, yeah, I'm definitely doing.
That's what we're talking, because
Because I need participants.
I need that, and like, I don't have the discipline to do it outside.
You do.
I do.
It's like a week of studying, which is more than I do in like a month for that.
Let's see, so you want 560.
We just do all that.
Oh,
Like three.
we should be able to play like soccer.
Are we doing your playing a lot?
Yeah, the APs on the side.
Stable, bro. We've literally never done it.
We're gonna have to
Except for last, except for last.
Absolutely nothing.
All right, guys, we're gonna do our second to last lesson. It's fairly short. So we'll get that done and then you guys can work on whatever you need to get done. Don't forget you have a problem set due today. So that's one thing you could be working on once we finish this lesson, but you could do something else too. So second to last lesson, we're looking at what are called norms and condition numbers. Mostly these things have to do with taking sets of data and doing approximations and things like that. So with norms is what we're going to look at first. When we multiply two vector or a matrix and a vector, sorry. When we multiply a matrix and a vector, we get another vector. So like here we would get 2, 6. Okay, and then I graphed both of those vectors, and what we see is, unless it's an eigenvector, it's going to change the direction, but it's also going to kind of stretch the vector's magnitude. Okay, and the norm has to do with how much that's going to happen. Okay, so a matrix has a norm. So when we talk about norm, we're talking about the matrix, and we're trying to figure out like how much does it change the magnitude of a vector when I multiply. So it won't always change it by the same amount, right? It's not a constant multiple that you're going to get, but kind of it's like an approximation of about how much the stretch is going to change. So if I take the same thing and I multiply the same matrix by a different vector, and again graph it, and we see again it's stretched 1, 1 to 2, 3. And so we could try to look for a pattern of what's happening by just multiplying a bunch of these things. Here I'd get 212, which is off the page. 12 is right there. But what I'm seeing is it's always making it larger. And the norm has to do with how much larger is it making it. And the norm is more of kind of a maximum stretch that could occur. So I'm not going to find vectors where this is going to make it like 10 times as long. There's some maximum length that it's going to make it a certain times as long that we're getting here. And so the norm is referring to the maximum stretch a given matrix can cause. It's similar to the idea of length of a vector. So norm is often the way we describe the magnitude of a vector is also called its norm. Well, the norm of a matrix is a similar idea. It's basically, think like when I multiply, what's the maximum magnitude change that could occur? And so what we're looking for by definition is the maximum ratio of AX, the magnitude of AX to X. Okay, these are just vectors here. AX is a vector, X is a vector. Those are the ones I just graphed on the previous 3 pages. I graphed AX and I graphed X, and I graphed AX and I graphed X, and I graphed AX and I graphed X. If we found the magnitude of all the AXs and the magnitude of the X's, and we start dividing and we start looking for a pattern, what the norm refers to is the largest possible ratio that could occur there. Okay, we could find this using calculus. We're not going to because there's easier ways to do it, but by definition, that's kind of what you'd be doing. We would end up with this function that we could use partial derivatives, and we could find the maximum value. But as with most definitions in math, mathematicians over the years have found other ways to do it, proven that these ways work, and they're simpler than that. So with calculus, what we'd have to do is we would come up with a function for this, right? So x would be like xy. Ax would then be 2x, 3y. And then what we do is we'd find the max of this kind of 3-dimensional function. Magnitude of ax is the square root of 4x squared plus 9y squared. Magnitude of x will be the square root of x squared plus y squared. And so we could find the partial derivatives, set them equal to 0, do the second partials test, find the maximum. Problem is that's pretty difficult even on this problem, and I picked a pretty easy matrix. I picked a diagonal matrix. It doesn't have, only has an x in the first element of ax. It only has a y in the second one. So it made those magnitudes pretty simple. They could get a lot worse, right? If I had something other than a diagonal matrix, I'd have more stuff here, which would make this part much more complicated. So this could get pretty difficult. So what people have found and proven over the years is, one, the norm of a diagonal matrix is just its largest entry, absolute value. So if it's a largest negative, that's okay too. So like for our example that we just were looking at, the norm of that matrix is 3, 2, 0, 0, 3. It's a diagonal matrix, so its norm would be 3. Okay, so if you saw one on the homework or on the test and it was 2, 0, 0, negative 7, you don't really have any work to do. The norm is 7. Okay, again, take the absolute value of all the entries of a diagonal matrix and pick the largest one. 2 and 3 are pretty much the same thing. Positive definite matrix is a symmetric matrix with positive eigenvalues. So all you do is you just pick the largest eigenvalue. Will be the norm. If it's not positive definite, but it's still symmetric, you just pick the largest absolute value eigenvalue. So if, again, this one, if you had a symmetric matrix that wasn't positive definite, it means its eigenvalues are not both positive. So you had a -5 and a 2. Well, then the norm is 5. It'll be the absolute value of the largest eigenvalue, or take the eigenvalues, take their absolute values and pick the largest one. With positive definite, we don't need the absolute value part because they're all positive, so it doesn't really matter. Okay, but 2 and 3 are pretty much the same thing. 4 is what we'll probably have to use the most because 4 is just dealing with any other matrix. Okay, if it's not symmetric, the norm could be an eigenvalue, but it's usually larger than both. So what we do is we use a property that we've looked at, I think, in like lesson 3, it'll be the first week of the semester, is even if A is not symmetric, A transpose A is symmetric, and it'll be square, and it'll have eigenvalues and all that stuff. Okay, but what will happen is the norm of A transpose A will be the norm of A squared, right? I basically have multiplied A by itself when I do that A transpose A. Or that's like, if it were vectors, that's a dot product, kind of multiplied there. So this is basically multiplying them together. So what A transpose A, its norm is the norm of A squared. So it'll be symmetric. So we just find the eigenvalues of A transpose A, pick the largest one and take its square root. So we'll do the square root of the largest eigenvalue of A transpose A is the norm of A. Yeah, A transpose A should give you a positive definite matrix. So but yes, it's absolute value. You pick the largest, ignoring negatives. Yeah.
So are those the same things as like magnitude sign?
It's similar to the magnitude. Yeah, it's the same symbol.
Same symbol?
Same symbol. And it's a similar idea, but it's, magnitude of a matrix doesn't really make sense. It's the norm.
Okay.
But yeah, it's the same symbol. It looks a little weird, huh?
Yeah.
It looks like they're off. But yeah, it's the same symbol. It shouldn't be any different. I don't know what happened there. It's probably Microsoft Word auto-correcting something, thinking all sorts of things. It definitely does look off center. But they don't really line up there. I don't know why, but yes, it should be the same symbol. Yeah. Okay, so that's all we'll do to find the norm. If it's diagonal, you don't have to do all this. If you do, you'll still get the same thing. But like if it's diagonal, you literally just pick the largest entry. If it's already symmetric, again, you don't really have to do this, but you'll get the same answer if you do. But if it's already symmetric, you just find the eigenvalues of the matrix itself. We don't have to do the ATA part. So all we'll do though, the formula that will work for all matrices is do A transpose A, find the largest eigenvalue and take its square root. Okay, and that'll be the norm. That's basically, again, kind of the maximum stretch that occurs. So if I get a norm of 5, then when I multiply that matrix by a vector, I could get vectors up to 5 times as large as the one I'm multiplying. Okay, that's basically what this is telling me. It won't always be 5, but it'll be up to 5, meaning I'll never get one that's like 6 times as long. If I got a norm of 5, that's going to be the maximum magnitude change that could occur. Okay, but all this stuff is stuff we've already done. So you're just putting these things together. We've done A transpose. We've found eigenvalues. We've found eigenvalues of symmetric matrices. none of this stuff is really a new, different thing. It's just using stuff we've already done for a different purpose. Okay. Condition numbers have to do with rounding. So think if we do collect data and are solving a problem. Okay, this, I don't know why I put it in this order, but this is kind of, this would probably symbolize your actual data that you collected. That say I'm trying to solve 1.001 times x equals 2.001. And I'm trying to find a solution. Here is the solution. We don't normally already have that, but say I already solved it, it's 1, 1. Picture is a large set of data and we're trying to solve, and we want to make it as easy as possible. And we see numbers like this. Like, well, why don't I just round that to 2? Okay, and then solve for 2 instead of 2.00001 or whatever. What the condition number tells me is if I do little rounding like that, how much will that throw my solution? X being the solution, right? X is what we're solving for usually. How much will that change the solution? And if we look, that actually made a pretty big difference, right? If I like graph these solutions, they're not really that similar, right? I just changed 1/1000th of one element of B, and I got a vector that's totally different. Okay, the condition number kind of tells me if that will happen or not. Like, you know, I would hope to see if I just rounded this by 1,000th, my vector would be just a little bit different by maybe a few thousandths or something. That's kind of what I'd be hoping to see, is it's not really going to make a huge difference. Here, I would say it actually made a pretty big difference considering it was such a small rounding by just 1/1000th, caused the vector to completely change direction, change magnitude, all that stuff. So the condition number helps us know if that's going to happen. Okay, and again, the condition number would go with the matrix, the coefficients of my system of equations. Okay, once I have those coefficients, they would kind of be assigned a condition number that would tell me if I start rounding my B values, what's on the other side of the equal sign of my system of equations, if I start rounding those, how much is that going to mess up my solution? Okay, that's what the condition numbers tell you. And again, in like a 2x2, we could just do it and probably figure that out. But in large systems of equations, this would help me know like how much rounding can I do to B to keep myself in an okay spot there. And so it's basically going to be our solution error. Again, that's the error to X. X is the thing we're trying to solve for. It'll be less than C times the error on B. That's our rounding, how much we've rounded. Okay, C being this thing called the condition number. So say C was 1,000 and I rounded thousandths off of B. My error in my solution could be off by full units. 1,000 times the thousandths that I'm rounding could cause errors of a full units. Okay, or say my my C was 2. Well, then if I round by thousandths, I could be off by 2/1000ths on my solution. And that'd be more like what I'd be hoping would happen, is just rounding some thousandths over here will just make my answer off by a few thousandths. Versus if C was 10,000 and I round thousandths, I could be off by tens on my solution. Okay, the larger C is, the more making tiny little rounding changes to B. If B was 2.035 and I wanted to round it to 2. If C is very large, rounding off that 35 thousandths could cause a big change. Okay, we get the condition number by multiplying the norm of A, which we just went over how to find, and the norm of A inverse. Now, once I found the norm of A, finding the norm of the inverse, I don't have to redo all the work. What we'll see is that, you know, say A was symmetric or A was diagonal or whatever. then all we're doing is finding the eigenvalues of A. Okay, if it's not, then we'll do A transpose, but it's a similar idea. So eigenvalues of A. So say we find them and it's lambda 1, lambda 2, lambda 3. Okay, however many of them there are. The lambdas of the inverse of A, we don't have to redo that work and find them. It'll actually just be the reciprocals of those eigenvalues. And I can't remember if this has come up in any problem set or anything like that where you saw that relationship, but it's just going to be the reciprocal. So I don't have to redo finding the eigenvalues and things like that. The norm of A and the norm of A inverse, you're basically going to take the reciprocal. You just have to look for one thing. In norm of A, we're doing the largest eigenvalue of A transpose A. You would want to take the smallest one and find its reciprocal to get the norm of A inverse, right? Because the smallest eigenvalue of A, the reciprocal will be the largest eigenvalue of the inverse. You don't want to take the same one and just take its reciprocal. So for example, say I got 1, 3, and 5. 5 is the largest eigenvalue of A. You don't want to take the reciprocal of that to get the largest value of the inverse. You would take the reciprocal of 1. Right? I would have 1 over 1, 1 over 3, and 1 over 5. The largest eigenvalue of the inverse will be 1 over 1. My smallest one of A will become the largest of the inverse. So once I kind of find the condition numbers by finding those eigenvalues, I pick the largest one for A, pick the smallest one, take its reciprocal, and that'll be the one for A inverse. Okay, so you don't have to redo the whole thing. So picture we've seen this on a test, right? I have problem 1, here's A, find its norm. Problem 2, what's the condition number? Take the thing you found in 1 and the work you used in 1 and you just have to do a reciprocal there. You don't have to redo the whole problem or whatever. Okay, this will be called the condition number. So we go back, generally large C's are bad things. Large being a relative term, right? If you're doing some sort of data and it's like, this is a statistic per 100,000 people. So like if you look up any like, in this year, we've had all this like COVID data being thrown at us. A lot of it is like a rate per 100,000 people in a state or in a city or whatever. Well, then if you're off by a few people, probably not a huge deal if it's per 100,000. But in other cases, like you may not want to be off by whole units. So C is pretty relative in terms of what we mean by large. But here, A is symmetric. So all I had to do was find its largest eigenvalue. I used a calculator because it's got decimal numbers, and that would be hard to solve some quadratic there. But it's symmetric, so I found its largest eigenvalue was 2.0005. Okay, then all I did to find the this is then its norm is the largest eigenvalue. All I did to find the norm of A inverse was I found the other eigenvalue, which is the trace 2.001 minus the large eigenvalue. And then I got the 0.0005. And then I just took its reciprocal. So I found the smaller eigenvalue of A, take the reciprocal, that's the larger one of A inverse, that's the norm of A inverse, which is 2000. Okay, A inverse has a very large norm. Multiply those together, I get 4001. I would consider that a pretty large C, but again, relative. If I now round by 1,000th, right, on B, I go to B and I'm just gonna round this 1,000th off of there. It could make my X's be off by a magnitude of 4 units. Okay, up to 4-ish units, right? Because I've got 4,000, my C is 4,000. I'm rounding 1,000, then it could cause me to be off by something close to like 4 units. Which again, depending on the situation, maybe you don't really care. 4 units is not that bad if I'm dealing with millions of people or something. 4 units may be bad if you're in an engineering situation. You don't want to be constructing a bridge and be off by 4 feet. That would be bad. So different situations might mean 4,000 is an acceptable number. But what it would tell me is round by thousandths, be off by full units. So maybe I don't want to round by thousandths. I want to leave those on, or I want to be even more exact and leave exact values. So that's kind of what the condition number would tell me here is. Again, large is relative, but this would tell me small changes to B could cause fairly large changes to X, my solution. If my C was like 4, it wouldn't. Okay, 4 is pretty small, so small changes to B will probably make small changes to your solution as well. Okay, so this is what we mean by error. It's like a relative error. So C is our condition number. So like here, that would be your 4001. C would be the 4001 in this situation. Error, that would be the magnitude of the error to B, meaning subtract your two B's, your rounded B, your other B, find the magnitude. So here that would be the 1/1000th, right? If I subtract, I'll get 0 and 1,000 would be my vector. The magnitude of that is 1,000. So my error here would just be the magnitude of 2.001 minus 2. And then B itself would just be 2.001. I'd find its magnitude. So it'll be a relative error times 4,000. So even though 4,000 is very large, that thing's gonna be pretty small. This relative error that we're looking at here times 4,000, that'll give me the worst case relative error to X, my solution. So what we're talking about is not rounding the coefficients of our system of equations. We're talking about rounding the B, the part on the other side of the system of equations. We're saying if I have some decimal numbers over there, can I just round those off? What's going to happen? This gives us kind of our worst case scenario, the maximum error that could occur then in my solution. And then you could kind of determine if rounding makes sense in that situation. Okay, I need to be super accurate. This is going to cause pretty big mistakes, so I'm not going to round. Or I don't need to be accurate. I need to be within 1,000 people. This is only going to make me off by a few people. I'm fine with that, and I can just round that number. Okay, that's kind of what the condition number tells me. Large condition number, large mistakes with small rounding. Small condition number, small error with small rounding. Okay, and that's it for today. So if you guys have any questions, you can ask those. If you don't, you guys have a problem set due today, you could work on that. You can work on something for another class. You guys can just go to lunch early or whatever, and I'll see you guys tomorrow.